Without further ado, I'd like to introduce the speakers for today. I'm Gaurav Deshpande, the Vice President of Marketing for TigerGraph. Main speaker for today is Dr. Victor Lee. Victor Lee has a PhD in computer science. His entire work has been focused on graph-based computing. So you couldn't have a better speaker to talk about what accumulators can do, especially when combined with massively parallel processing, which is a unique strength of TigerGraph as the only scalable graph database for the enterprise. Let me quickly cover what we do in terms of use cases briefly. You never buy a technology for the sake of buying a technology. You always buy it for a reason. You buy it either to increase revenue, to reduce costs, to manage risk more effectively, and you also use it for improving your operational efficiency. So in order to get all of these business outcomes, we have specific business use cases and solutions that are part of each of these outcomes that are helping you achieve these outcomes. So recommendation engine, real-time customer 360, product service marketing, all of these will help you increase your revenue. Fraud detection, anti-money laundering, risk assessment and monitoring, cyber security, these typically use cases are the sample use cases that you would use to reduce your costs and manage your risk. Last but not the least, in order to improve your operational efficiency, you're typically looking at establishing an enterprise knowledge graph, looking at ways to optimize your network, IT, and cloud resources, looking at building out energy management system, efficient energy management systems if you are in that industry, and last but not the least, the supply chain analysis. Along with those, there are a set of foundational use cases like geospatial analysis, analysis of time series data, and of course, AI and machine learning that is a foundational use case that pretty much weaves into every single use case here. You can find all of this information on tigergraph.com. If you click on solutions, you will find information of these use cases. Briefly, 3 customer examples. Wish.com, which is a startup that is competing effectively against Amazon and growing very rapidly. In just 3 years, they crossed $1 billion in revenue. They are several billions of dollars in revenue now. Their recommendation engine is built on TigerGraph, and you have several Graph Gurus episodes that cover that. We'll also talk about how accumulators are used as a part of the recommendation engine today. The second one, China Mobile. We have several telecom customers. China Mobile is the largest mobile service provider in the world. They detect frauds in real time using TigerGraph. Last but not the least, Visa is optimizing their network and IT infrastructure and minimizing outages using TigerGraph. So this is 3 examples of 3 customers that are transforming their businesses with TigerGraph. Now, without further ado, let me hand it off to the primary agenda for the webinar here to Dr. Lee, who's going to cover certain charts for you. So he's going to quickly share his screen. Let's give it a moment, and then we'll begin that part of the agenda.
So I am really excited to be back here talking with you again. I've done probably the very first couple webinars, and I know we've had some other speakers such as Emma Liu, also on the product team, but since this is getting into the GSQL language, which is sort of one of my favorite topics, I'm going to be taking over. So we're going to talk about accumulators, and accumulators are one of these special features of graph languages, of the GSQL language, which we've had from the beginning. It's one of the things that really distinguishes GSQL. So first I'm going to talk about the basics of graph traversal and why when you do graph traversal, whether you are pattern matching or running analytics, running whatever type of query, you are in some sense traveling the graph, and why that always is a good instance for using parallelism. And then we'll talk about how accumulators naturally take advantage of that parallelism to do efficient computation, and then to really explain the idea of what is a GSQL accumulator through some examples and use cases. So let's look at a typical graph topology. This is showing a person, Lee, on the left, who has some friends or acquaintances. We show 3, and then each of those 3 persons also links to 3 more persons. So just in the simple example, each node has 3 neighbors. what you notice is that with the first hop, we have 3 edges. But when you get to the second hop, you now have 9 edges. So it's multiplying. So the more hops you have, the more effort there is to cover the graph traversal to understand what's happening. Because graph traversal is how you see the data. But notice also that in the middle, for example, the person R on the far left is linked to 3 other persons, Bob, Chris, and Sue. Whereas also Q is linked to 2 persons, Bob and Chris, and S is linked to Chris and Sue. So it's not just 9 edges connecting to 9 separate nodes. It's 9 which merge and overlap to create the 5 nodes. So there's some complexity, and that overlap, depending on what your use case is potentially very important, and you need to take that into account. In fact, that is what graph data is all about. Graph data is all about understanding the meaning behind connections. And when you have this shared friendship or shared association, understanding that is part of what you get out of graph. So hops are good, but the more hops you take, the more work is involved and the more complexity. To do your work efficiently, you'd like to take advantage of parallelism. So notice in that graph traversal, you're going from from Lee to each of its 3 friends. That's 3 separate paths. And then each of those friends has 3 more paths. So if you could think of those nodes as the persons themselves, you could say, well, I am handing off, I do the first hop, and then I hand off to let each of them do the next hops. So if you can take advantage of those nodes to do your work for you, you can get it done in parallel more efficiently, right? Bob, Chris, and Sue can all work at the same time to understand all of their relationships. You get the work done faster. So graph topology naturally lends itself to this division of labor. Now this is where we say, if that labor involves just even some basic type of computation or much more complex computation, it's really up to you. This is where accumulators can really offer you something. So what is an accumulator? Well, in its simplest sense, it's basically just a variable, a data variable, so you hold data in it. They are shared in the sense that multiple entities can access them. Multiple entities usually can write to them. So they're sitting out where multiple processors can see and use them. They're runtime, so they're created during a query. You don't have to, they're not necessarily part of the hard data of the graph, so you're not altering the graph structure. You're creating some temporary workspace to help you with your computation. So shared runtime variables for parallel processes, because those multiple workers can work in parallel and access the accumulator independently of one another, asynchronously from one another. And they have a built-in accumulation function. So they're designed to not just gather data, but to gather it in an intelligent computational way, so that gathering is actually performing some useful computation. They are used in a 2-phase process. So in the first phase, you send, the workers send messages to the accumulators. What are those messages? Well, the messages are data and some instruction for what to do with that data. But those multiple workers, so you can see down here I've got 1, 1, and 2. They are 3 pieces of data. They could each be sent in a separate message. So 3 different messages. So those values 1, 1, and 2 in some order end up in this input bucket for the accumulator. So notice the current value of the accumulator is 0. I've got these values in this holding bucket. They have not yet updated the value. And that's part of the flow to make this parallel processing work out in the end. Remember, I don't know what order those 3 messages are going to arrive because the workers all working independently, they work at their own pace. And the second phase is when you said, okay, all the messages have come in, I'm going to aggregate them in the way according to my type of accumulation that I've been told to use and update the value all at once. So I've accumulated 1, 2, and 1. I'm performing a sum operation. So the sum is 4, and I update the value to be 4. Now notice with sum, it doesn't matter in what order those values arrive. It could have been 1, 1, 2, 2, 1, 1. All of them add up to 4. So accumulators are designed to focus on these operations where the order doesn't matter. Mathematicians call those commutative operations. So addition is one example. Multiplication is another example. Building a set is another example, because by definition, the order of the items in a set has no real meaning. So again, let's look at accumulators from another example. Let's assume we have a classroom. Teacher has given a test. She gathers the test and wants to calculate the average score. So the teacher represents the node that has an accumulator. Each student is also a node. You could think of the test as nodes, but let's think of the students as nodes. And then, of course, there's a connection between students to teachers, the edge. So that's our basic graph. Here we'd have 1 node, 4 student nodes, and 4 edges. Now, we're going to do some accumulation. So each of the students turns in their test paper. So they're sending a message. They're sending the message to the teacher node. Each of those messages has some value, a test score. The teacher is performing the accumulation operation. So, and that operation is predefined. So gather the data, as you're accumulating it, perform the running average. And so when it's it's actually not, remember, it's not calculating on the fly. It's calculating, it's gathering, phase 1, gather all the test scores. Phase 2, assemble them all together and compute your average. What I meant by on the fly is if we decided to stop after 3 tests instead of 4 tests, it would work. If we decided to stop after 2 tests, and that would work. So it works for any size, but you do want to sort of define a limit. When does phase 1 end? When does phase 2 end? And that's built into GSQL queries. Those phases are very clear, and we'll see that in an example. So let's look at one other example. I hope you're following along. Some of you I know have looked at accumulators before. Maybe this is enriching your understanding. Maybe this will make it easier for you to explain it to someone else. Maybe this is your first time looking at accumulators. So we're going to look at a person and movie data set. So we have 2 types of objects. We have persons and we have movies. So what you want to do is you want to count the movies that your friends have seen. So you ask each of your friends to count up, to tally, how many movies have they seen in the last year? And since each of them is going to work independently and presumably at the same time, you've got parallelism again. So if you got lots of friends, they've seen lots of movies, that would take a lot of work if there was just one person who's trying to do it all at one time. But we've got parallelism. That's part of the secret of accumulators. So this you might call the data gathering phase. The second phase is when you consolidate those individual lists into one list. Now, if we're only counting, not recording the names, how are you going to eliminate duplicates? So again, let's say Bob counts 3 movies, Chris counts 3 movies, Sue counts 3 movies. That looks like 9 movies, but we know it's only 5. So if we're only working with numbers, how are we going to eliminate duplicates? So this is a classic problem in computer programming, and the classic solution is to use a true-false variable, a Boolean variable. We often call it a flag, and we often call it visited. And remember, we're talking about graph traversal. That makes a lot of sense. So when you think about visiting, think about I visit each of my friends to tell them I want to count. And then each of my friends, quote, visits a movie and counts the movie. And so the trick is you want to visit each movie only once. So we give each movie a flag, and it's initially false. Excuse me. So when a person visits a movie, they check the flag. If the flag is false, all right, you're allowed to process it. So the processing in this case is to count it, to add it to your tally. And when you do that, you need to also set the flag to true so that no one else will count that flag. So if somebody else comes along, they see the flag is true, so they don't do any work. They skip over that movie. So the end result is that you count each movie once. So again, looking at this movie in the center, I think we were calling that movie or item R before. So R is connected to 3 persons. Let's say Chris is first. So Chris sees the movie's flag is false. He raises it, he sets it to true, and Chris gets to count it. Then Bob comes along. Bob sees the flag is true. He doesn't do anything. Sue also comes along later, sees the flag is true. Sue doesn't do anything. So the movie gets counted once. Those of you who know programming, you know this, but now we're all on the same page. Very simple technique for making sure you count something only once. And it comes not only in graphs, but with graphs, you see why this is a very useful technique. So let's see how we use this with accumulators. So in our example, remember, what is an accumulator? It's a runtime shared variable which has some built-in accumulation or update function. So where do we want to use accumulators? So each friend, remember, is keeping count. That count would be a local accumulator. Local because each one has their own copy, each friend. The visited flag, the true-false flag, is also a local accumulator. And so each of the movies needs one. So, and the way that GSQL queries are designed, they have a built-in capability to say, this is what I want each friend to do, and it will naturally process them in parallel. So each friend can work at the same time. They can use these shared accumulators. Remember, from the perspective of these friends, that each of the friends has access to the flag, and so the flags are shared. And then finally, the last step would be to consolidate all the lists into one master list. And that would be a global accumulator because we only need one copy for the whole problem. It's shared, but even local accumulators are shared. But since we only need one for the whole problem, it's better to use a global accumulator. Now, if you think about it, we could do a little bit of an optimization. We don't even really need those local accumulators for the initial tallies. We could just have one tally, right? Since I said they're accessible to everyone, well, when Bob is going and counting his movies, he could just record them directly on the global list or the global count. Chris could do the same. Sue could do the same. So this eliminates the consolidation step, and you also end up using less memory because you only need one count variable instead of several count variables. We still have the parallelism. We're still taking advantage of accumulators, but we've reduced how many accumulators we need, and we reduce the number of steps. So this is a great simple optimization. All right, so now that I hope you hopefully understand the concept, I'm going to throw some GSQL code at you, but I think you should all be able to understand it. So first line, we define our query. We're going to call it friends movie count, and it has one input parameter, a vertex, which I'll call me as the name of the variable. I define my two accumulators. I have an OR accumulator for, that's the flag. So has a built-in Boolean function, and we initialize it to false. And notice the name of the variable begins with one ampersand, I think that's called. One means local. The second variable is a sum accumulator because we're going to be counting. And we're going to be just counting 1, 2, 3, so those are integers. And it has a double ampersand. Excuse me, that's not called an ampersand. I forget what those are called. An at or it's an at sign. So this has a double at, and that means global. So, and one more definition, I take the input variable vertex, I throw some brackets around it to say it's a set of vertices, which happens to just be a single item. So start is my initial set of vertices, and then I do a one-hop graph traversal from me to my friends. That's what this in blue says. From the start set, which is me, across friend edges to all the other persons connected by those friend edges. So we're just finding out who are my friends. So friends is the name of the collection of my friends. And oops, let me quickly edit this because that should here say from friends. You can tell I didn't actually run this code. Otherwise, I would have fixed that. So I go from my set of friends across these edges that say I saw a movie. And so M is the set of movies that my friends saw. This is on an individual basis. This is finding the 9 edges. So there are 9 edges which match this pattern from 3 friends, and we know there's some overlapping movies. So there are 9 edges, but it's not pointing to 9 different movies, it's pointing to 5 movies, if you remember our data set. And this is where I do the accumulation. So the accum clause. The accum clause is where you put accumulators to work. And so for each of those edges, each worker, whoever is responsible for that edge, is checking, is my movie, has it been visited before? If it has not been visited, then add it to the global count and set the flag to true so that nobody else counts it. And that's it. So that one condition to check if it's been visited before, and these 2 operations. So it's really, if we skip over the visiting part, if we skip over the overlap, there's just this one step, at movie count plus equal 1. That is how you do the count. And it's automatically distributed for the parallel workers. It happens we have 3 friends in our small data set. 3 is a small enough number that I'm sure there could be individual processes. There is a limit to how many processes you can have running in parallel in the TigerGraph system. We have a variable you can set to adjust that. A typical value is like 32. So if I have 1,000 friends, it doesn't mean they're going to be 1,000 processes, but there may be 32. Each of them is handling a fraction of the total work. You're still getting a lot of parallel processing out of that. So let's review what are the properties and features of accumulators. So there are 2 types of scope. You can have either local accumulators on a per vertex basis, or you can have global accumulators where there's just 1 copy. There are multiple data types and multiple functions available. We saw 2 types. We saw a Boolean one, true, false, with an OR function. The OR, in this case, since we're only setting it once, it's not really critical what the function is. And then we had, for the tally, we used an integer collector. We're storing integer data with a sum function. And we also saw that inherently, accumulators support this multi-worker processing for parallelism. Anyone can read, and anyone can say that they have an update. Remember, the update doesn't occur immediately. Everyone sends a message to say what they want to happen. The accumulator gathers all the messages. When did the accumulation actually take place? It took place at the sort of at the, you can imagine the end of this accum. After everybody has processed all their edges, the work is done, then the accumulation occurs. I mentioned there are several types. I'll just very quickly go over the multiple types so you can see that we do have a rich assortment. We use sum. So imagine you have these 3 input values. All of these examples use the same data, so you can compare what happens with the same data. All of them have the same input data, 1, 3, 5, and they all have the same initial value of 2. If you're performing sum, you add these values, you get 11. If you have a max accumulator, you take the maximum value that you've seen out of the entire history, so that would be 5. Min accum, the minimum value you've ever seen, so that would be 1. And average, as we can understand, average all the values you've ever seen, 2.75. So those are all ones that return a single value. We also have collection or container accumulators for things like sets, lists, maps, and heaps. So a set, remember the order of values doesn't matter. A set never has duplicates. If it sees a duplicate, it does not add a new item. It says, I already have that, I'm good. So if we're adding 1, 3, 3, 5, and we previously had 2, you end up with these 4 values. But again, I point out that the order is not significant. I could have written 5, 1, 3, 2. It would be considered the same information. A list accum, you do count every value and you put it in order. A map accum is accumulating pairs of key values. So a key, like 1, which points to a 2. And lastly, a heap accum, which maintains a sorted list. So you tell it how you want to sort the values. So in this case, we're sorting by that second numeric value. And of course, there's also, do you sort highest first or do you sort lowest first? And you also give a size, like it's basically what some people call a top K container. I want the top 3 values, or of the 3 biggest values or 3 smallest values. And it automatically does the sorting as you add new values. So I've gone a while. I want to show you a couple more use cases on the slides, and then if we're going to try to switch to another computer so that we can show you some live examples. Hope that works. So I showed you a simple example of just counting. I could have done accumulation, I could have done scoring, but it was from one origin point. Now, there are a lot of analyses and algorithms where you want to study the whole graph. A really well-known example is PageRank, where you're figuring out the influence or importance of each node in the graph, and the importance is a relative number. It depends on the whole graph structure. So you can't calculate PageRank unless you look at the whole graph. So that's computationally intense. I've tried to give a simple view of what work is involved. If I have a node V, the page rank of V is a function of the page rank of its in neighbors, those who point to V. So that's saying it's the sum of the page rank of A divided by the degree of A. Degree of A is how many out neighbors A has. So you see there's a factor for in neighbors and a factor for out neighbors. So it's basically, it's a ratio, it's a fraction of A's page rank plus a fraction of B's page rank plus a fraction of C's page rank. So since you're analyzing, just looking at this one formula, you can see we're doing summing. If you think, remember, think of each node or each vertex as a worker. So each one is sending to its neighbor a fraction of its score. That's a great opportunity for parallelism and for accumulation, because we're adding up these values. That's a form of accumulation. We also need to do that same thing for every single node, not just V, but A itself has to do that. B itself, every single vertex needs to do this. So two cases where you see accumulation and accumulation with parallel processing is really key to efficiency. Each worker, each node, to calculate its page rank needs to do some gathering of data, and every single needs to do that. So, and one other place where accumulators are used, the typical method for actually calculating page rank is the iterative method, where you start with some initial guess. Every time you run through this update iterative calculation, the values get closer to their true values. So you can initialize page rank. Let's guess that everybody has a page rank of 1. And then you run through this calculation, which updates everybody's page rank value. It's now a little different. It's now a little closer to the final value. You keep repeating this iteration until the values don't change much anymore. And that not much anymore is looking for what's the maximum change you saw for any of the nodes. Is that maximum change below a threshold you set? So that calls for a max accum. You compare the previous page rank with the current page rank, store that difference, throw that difference into a max accum. When you're done with one iteration, look at the value of that max accum, see if you've exceeded your threshold or not. So 2 opportunities for accumulators. I'm going to look at 1 or 2 more examples before we try to switch to our live demo. Got my fingers crossed, and then we'll be happy to take your questions. So 1 more here. I've got movie recommendation. This is sort of an expansion of the one that I walked through with you. This one was actually presented in detail in Graph Gurus 3. So if you want to look back on our YouTube page, youtube.com/TigerGraph, you'll find all of our past Graph Guru webinars and plus some other webinars. So in this case, person has rated these movies in red, figure out who else has rated those movies, and then what other movies did they see, and which of those other movies have strong ratings, then recommend those top-rated movies back to me. So this is what's called collaborative filtering. Here's my tastes, the things I've seen and liked. Who else has seen those same things and rated them similarly? So those persons have similar taste to me. What else have they seen? And which of those had high ratings? So if you go online to look at the code, you'd see where we have several different accumulators, but you can see that calculating comparing my taste to somebody else's taste, we use what's called cosine similarity. So you're squaring numbers, you're adding numbers, you're doing division, you're adding up the contribution from each of the movies. So there's accumulation there, and because there's several movies, several friends, there's more accumulation. One more case I talk about here we have live 5 different use cases running on some Amazon instances on the cloud where you can try for yourself. If you haven't tried out Test Drive for yourself, you can go online, but we have one for anti-fraud, and that shows some more cases. This one that I would like to show you is gone in detail in Graph Gurus number 4. And we're going to try to switch computers now. So hang with us for a minute.
Looks good.
Great. Okay. So this is testdrive.tigergraph.com. 5 different cases here. One is anti-fraud. There is little video to describe each of them, but I'm just going to go directly to this. So this is Graph Studio. This is the visual front end for our products. You can design a graph solution and run it from here. If you haven't seen this before, you should really take some time to look at one of our videos. But these are preloaded. The test drives are preloaded with several queries. The one I want to show you is called circle detection. And if we expand the code here, I see 1, 2, 3, 4, 5 accumulators. Ooh, more. 6, 7, 8, 9, 10, 11, 12, 13, 14. It may look a little intimidating. And that's because we try to write a very efficient query, a high performance query. We're looking for a path that happens to make a circle, and each of those edges, I'm going to show you what it does, and then we'll come back to how it does it. Let's see, so one vertex. Okay, modest answer. And is this the one I was?
Just to add a little bit of a color to what Victor is showing. So this is in real time detecting loops in terms of money laundering and fraud. So it's going in real time and looking across multiple hops. The first one was, which Victor said was a modest one, had about 8 or 9 hops. And we have seen as many as 20 or more hops that are covered in real time using the combination of accumulators and TigerGraph's massively parallel processing engine. So I'll let Victor speak to what I call the spaghetti of money laundering.
Yeah, the spaghetti nest. So again, this data set has about 1 billion vertices and 5 billion edges. So, you know, we traverse that in a fraction of a second. What it's showing us is all the instances where you start from one node, travel across some money transfers. The red dots are persons. They connect to a transaction and then back to a person. So it takes 2 edges to get from one person to another person where they have passed money. And the requirement is that these loops have to, the transactions have to be forward in time. Because what we're looking for is money passed, I passed A, call me A, I passed money to B, and then B passed some money to C, D, E. Somewhere along the way, it loops back to A. So it's a forward loop in time, and that's one of the restrictions. And to do it more efficiently, we actually check in both directions and try to meet in the middle. Because of the way that, you know, remember we talked about how with each hop, you're doing more work. So if I have to go 10 hops, by the time I get to the 10th hop, there's a huge number of edges. But if I work from both ends, then I have 2 cases of 5 hops, and 5 hops has fewer edges than 10 hops. So it's actually more efficient to work from A forward in time and also A backward in time and see if I meet somewhere. And because remember, there are many different transactions. A is not a point in time. A is a person. So if I go back to the query, and again, I'm not going to walk through this in detail, but just to kind of show you the many different types of accumulators and why they were used. So you see left and right, that has to go forward and backward in time. If we were to just do it the simpler way, we could eliminate several of these. So the problem isn't really that complex. Maximum rank, because we're looking for the ones with the most money transferred, we're not showing all the possibilities. List accum, because we're building up a path and we need to record the path somehow. So a path is a list, right? You make a list of edges. That is what we're showing. And notice it's even a nested list of lists. So it's like an array. So there's really, with the set of accumulators, the different types of accumulators we provide, the ones for simple arithmetic, sum, min, max, the booleans, or and, the collection ones, set, list, map, heap. There's a huge number of things you can do. There's really, remember, GSQL is a Turing complete language, meaning that anything that you can do for programming language in general, you can do with GSQL. So I'm going to wrap it up there and see if we have any questions. I just want to summarize. I did have some more examples. I said on Test Drive, but I would invite you to explore on Test Drive on your own. And if you have questions about those accumulators, come to us and we'd be happy to answer. So, in summary, graph traversal and graph analytics can be complex due to the structure of graphs. That's why they contain so much information. Graphs are great because they are information rich, but that's complexity. So on one hand, it's complex, but on the other hand, the benefit is that it's amenable to parallelism. So the GSQL language, in particular accumulators, coupled with the TigerGraph platform with the massively parallel processing, really give you a simple and efficient way to do parallelized aggregation and computation. So you've got the graph, you've got the potential to do great things, but you need the right tools, and accumulators are one of those tools to help you do that work efficiently. GSQL has a variety of different shapes and sizes accumulators to fit all your different needs. Want to thank you. Open it up for question and answer.
Yeah, I'm going to give everybody a moment to type in their questions. I have 2 questions here already. And as I talk through those, please ask more questions. Feel free to ask more questions of Dr. Lee, either now or later. His email address is always victor@tigergraph.com, or me, Gaurav Deshpande, Gaurav, G-A-U-R-A-V @tigergraph.com. The first question is about memory consumption impact of accumulators. So do the accumulators increase the memory footprint? What is their effect on memory consumption? That's the first question, Victor.
Sure. Well, as I said, accumulators are temporary storage. So when you define them at the beginning of a query, you are reserving memory. And then when the query ends, they are deleted and deallocated. So while the query is running, you are using more memory. It's just like any procedure. And again, if you've done some programming, you know that you're defining variables for a procedure. Those variables are going to use up memory. But if you have an efficient system, then they get deallocated when they're no longer needed. So it's the same thing.
Excellent. I have a second question here. Second question is about computing and parallel threads. Is there a limit to the number of parallel threads? Is there an optimal number of parallel threads that's recommended for use with accumulators? How does that affect the computation capacity, either on premise or in cloud? So that's the question.
Sure. One thing that is a factor is how many CPU cores you have. So that's kind of what provides the hardware capability for what you're ultimately doing. Even if you create a software thread, you still need a piece of hardware to do the actual work. So the more CPU cores you have, the more, we call them workers, the more workers you can support. So We usually, there's a default setting, and I don't remember. I said earlier that I thought it was 32. You can go a little higher. At some point, there maybe the overhead might tend to cause some roll off in the gain. And again, if you don't actually have the CPUs to support the work, then you're not actually getting any benefit. So those are the factors. I think around 32 is good for most cases.
Okay, the last question here. You mentioned PageRank as one of the algorithms that accumulators are used for. Any specifics that you can share of performance improvement for PageRank for TigerGraph? Can you quantify that a little bit more? You mentioned that PageRank is intensive, so I guess the question is about if the PageRank is intensive, is there anything specific about TigerGraph, any specific details that you can share?
Yeah, I recently ran across a benchmark report that was published on DZone. Let's see if I can find it right now. It compared TigerGraph with Neo4j on PageRank. And we have our own benchmark report, but this is a third party, so maybe you might find that a little more to your liking. Here we go. So here were the queries. PageRank query performance. TigerGraph completed in 3 hours. Neo4j did not complete within 24. If we go back to see what were the systems, the data, 500 million vertices, 19 billion edges, one Amazon EC2 instance. You see the 16 CPU cores, 122 gigabytes of RAM. I was looking at the product versions here. So this is the TigerGraph Developer Edition, which you can download for free. The Developer Edition has the exact same engine as in our Enterprise Edition, so it's the same performance. This is compared against a recent Neo4j Community Edition. Another thing I'll add, in order to compare against Neo4j, we had to do it in a single server. TigerGraph is distributable. In our benchmark report, we show how the performance increases when you can distribute the same data across multiple servers. So this is not replication. I'm taking one copy of the data and spreading it across multiple servers. And because I essentially have more parallelism, I can do the PageRank query faster. 8 servers, I can accelerate by 6.7 times. That's what it shows in our benchmark report. So, and lastly, I'll mention that our PageRank query, it's just written in GSQL. It's not even tuned. Neo4j has their APOC library, which is great, but they have to handcraft all of those to try to, it's a benchmark. So they're going to do everything they can to get optimal performance. Ours is just a GSQL query written with the same language that's open to you. No special effort to optimize it. That's just the natural performance of our platform.
Okay, one more question here. Last one, I promise. We're running out of time. Is there can you share where the open GSQL library is for the developers?
Sure, for the graph algorithm librry?
Yeah. It just says GSQL library, so I'm assuming they're talking about graph algorithm library.
Yeah, let me see. I'm going to go to our documentation first. So docs.tigergraph.com. You see right at the top the GSQL graph algorithm library. So this here, it tells you what we have available. And then there you also see a link to our GitHub repository of algorithms. So I'd say, if you can't remember all the detailed links, just go to docs.tigergraph.com and you'll see everything that we've got.
Excellent. Thanks a lot for everybody taking time out of their busy days to join us. I'm very excited to announce the next topic. We'll soon send out a communication about that. We will be doing a drill down on Customer 360, specifically on healthcare, but it will be applicable, presented in a way that will be applicable for non-healthcare people also. So if you are looking at a Customer 360, a customer journey, if you're considering that, you don't want to miss the next one, which will be in 2 weeks. Last but not the least, a lot of you have been joining this office hours. It's become a huge hit, so we are continuing it. We might expand it in terms of time frame in the coming months. Every Thursday, remember, every Thursday at 11 a.m. Pacific, 2 p.m. Eastern, you can directly talk to engineers. Dr. Mingxi Wu, who was in part wrote a large part of TigerGraph, including GSQL, is there most of the times. We have our ACE data scientists and developers available for answering your questions about data modeling, about GSQL queries, about optimizing queries. And a lot of you have been taking us up on that. We're starting to run out of the 1 hour time, so we might extend it in the future one or schedule other ones, other days. But for now, we're sticking with the Thursday, 11 a.m. Pacific. So please bring your best questions and your queries about TigerGraph, and we would help to build the next innovation application, whether you're building it for your own startup or you're building it for an enterprise. Thanks a lot, and have a great rest of the day.